So this is going to be over 13.5, curl and divergence. Let's talk about curl. Let's say we are given some function of 3 variables, a vector function parameterized by functions component-wise of 3 variables. P, R, and Q. All right. Let us define what we mean by the curl of F. Curl of F is defined as the del operator cross the function. Clearly, this is the cross product between 2 vectors. Therefore, the output is going to be another vector. And what is it defined by? It's defined by a determinant I, J, K. And what is the del operator? This is defined as partial x, partial y, partial z. So when we take the cross product, we have I, J, K. And over here, we're going to have partial x, partial y, partial z. And then for F, we'll enter the entries P, Q, and R. Okay? So what do we get here? We get I times the determinant partial y, partial z, q, and r, right? And then for j, we say minus j hat, we get the partial x, partial z, p, and r. And then plus k hat, the determinant partial x, partial y, p, and q. All right. This right here ends up becoming I hat times partial r, partial y, minus partial q, partial z. This becomes minus j hat times partial r, partial x, minus partial p, partial z. This becomes k hat, partial q, partial x, minus partial p, partial y. And that is exactly what the curl of F is. Component-wise, the curl of F is equal to partial r, partial y, minus partial q, partial z, comma. Let's distribute that negative, so this becomes partial p, partial z, minus partial r, partial x, partial q, partial x, minus partial p, partial y. That is the vector. So maybe on your formula sheet for this last exam, I would like you to understand how this is derived, right? You clearly take the cross product, and that's what it is. For your formula sheet, you might want to put this down there, so you don't have to redo this on the test. But you should, you don't have to, but you should, as I keep trying to teach my students, you should know where this comes from. It's very clear that once you do the computation, this is what you get. But if you're given a vector and we say calculate the curl, that's really all you need. But if you weren't given that and you had forgotten it, let's say you don't get a formula sheet and you forgot what that is, I'm not going to memorize that. Neither should anybody. You can do this and get to that. So theoretically, all you need to know is this. Practically, on a time-constricted exam, this will be really, really helpful. But make sure you know where it comes from. All right. Now, let's actually apply it to a concrete example. What if our f of x, y, z, our vector in 3 dimensions, is parameterized by xz, xyz, and a minus y squared? What is the curl of f? Well, it's partial. So r, it's going to be r, it's going to be pqr. So partial r, partial y, is just minus 2y, minus partial q, partial z of this is just an xy. Moving on. What's partial p, partial z? Here's partial p, partial z is x minus. What's partial r, partial x? 0. What's partial q, partial y? Partial q, or partial q, partial x. Partial q, partial x is yz minus what's partial p, partial y? 0. So this becomes negative 2y minus xy, comma x, comma yz. This is equal to the curl. Why do we call it the curl? What does it mean when something curls versus just being straight? It bends, right? The curl is actually measuring how much bend there is in a vector field. Really. So in a vector field, you know, it forms like all these lines and whatnot, vectors. So if the vector field is rotating, you notice there's a spiral in it, it will have a non-zero curl. But if you see that it doesn't have any spirals and all the vectors are going either out of one point or in one point, like in the gravitational field, all the vectors point towards the center of mass, there is no curl. How does it measure that? Well, remember that the cross product creates a binormal vector, a perpendicular vector to both these vectors. And because it does that, your vector field is f. How it's changing is the gradient. And so you know that f and how it's changing, what's perpendicular to that is where it's going to move. Isn't that cool? Yeah. Yeah. Yeah, so this mathematical abstract concept actually relates to curling of vector fields. So here's a claim that the curl of the gradient of f is equal to 0. Why is this the case? Let's prove it. Okay, this is the same thing as Is it not? And so that is the same thing as I, J, K, but I'm not kidding. Partial X, partial Y, partial Z for the del operator, but then the gradient is partial F, partial X, partial F, partial Y, partial F, partial Z. So this becomes partial Y, partial Z, partial F, partial Y, partial F, partial Z, minus J hat times partial X, partial Z, partial F, partial X, partial F, partial Z, plus K hat, partial X, or partial X, partial Y, partial F, partial X, partial F, partial Y. So then this equals I hat times partial squared F, partial Y, partial Z, minus partial squared F, partial Z, partial Y. This becomes negative J hat, partial squared F, partial X, partial Z, minus partial squared F, partial Z, partial X. This becomes plus K hat, partial squared F, partial X, partial Y, minus partial squared F, partial Y, partial X. Now, Clairaut's theorem states that if you have a nice function this is true. Okay? Meaning these are the same thing, so this becomes 0. These are the same thing, so this becomes 0. And these are the same thing, so this becomes 0. So by definition, what we have here equals a vector in which each component is equal to 0. And that is by definition the 0 vector. Okay, so let's talk about, so now we know that the curl of a gradient is 0, the 0 vector. Let's talk about how does this relate to conservative vector fields? Vector fields in which have a potential function whose gradient equals the vector field. Vector fields who only take the line integral inside this vector field, that it only matters about what the values are at the endpoints. That's why we care about conservative vector fields. That the line integral inside this vector field behaves like normal integrals, whereas your antiderivative at the endpoint minus your antiderivative at the starting point. That only happens in conservative vector fields. It does not happen in general. So remember that if F is conservative, vector field, this implies that there exists some potential function F such that gradient of that F is equal to your vector field. So notice that if the gradient of f is equal to your vector field, this theorem that we just proved, that the curl of the gradient of a function is equal to 0, that allows us to say, oh, well then the curl of a conservative vector field is equal to 0. That's why the gravitational force is a conservative vector field. Because notice that, let's say here's our planet Earth. The gravitational force just points the same in all directions. There is no curling of the vector. Because if you draw straight lines, the vectors all in a straight line radially line up with this central dot. If they were doing some funky stuff where instead of that they were doing this, this would have a non-zero curl. You see that? Because the vector field seems to be twisting. So this would have a non-zero curl. So clearly, if you have a non-zero curl, the vector field can't be conservative. So our vector fields are only conservative when we have non-zero curls. Isn't math cool? Not only is it cool, not only is it beautiful in its own right, it is very practical. Well, at least us mathematicians can make it practical if we want. We don't have to. Actually, we're usually forced to. Society's like, hey, you want us to like pay for your living and whatnot? Do something useful. So when they poke us with the stick, we produce this kind of stuff, which is very useful. But we also think it was cool in its own right. There are some mathematics who people don't even know how it could be useful, but they invent it anyways. This is what pure mathematicians like doing. We invent math just because we feel like it, just because we can, just because it tickles our fancy. So, I don't have to convince you to be a math major. You're already a math major, but I get to nerd out with anyone who is an aficionado of this beautiful subject. So let's show that this is not conservative. How do we show that it's not conservative? Well, that theorem that we had earlier stated that if conservative, that implied that the curl equal to the zero vector, right? The reason we got that was because if it was conservative, then the curl of the vector was the same thing as the curl of the gradient. And we calculated that no matter what, that the curl of the gradient is equal to 0. And if you have a conservative vector field, then the gradient of a potential function is your vector function. So you get to it buys you that it equals 0. We took the curl of this function in the past, earlier this class period. What was it? It was non-zero. It was negative 2y minus xy, x, y, y, z. So this doesn't equal the 0 vector. Except trivially, I guess, at the origin, but not all throughout the space. So it doesn't equal the 0 vector. So with that theorem, we can say because the curl of this vector is not 0, then it cannot be conservative. Very much like how this white vector field versus this orange vector field show a conservative or a non-conservative vector field. Sometimes conservative vector fields are called irrotational vector fields because you don't see any rotation in the vectors. So what can we say? Well, what is our conclusion? That you take the curl of your vector field and it equals 0, you can say that that is conservative. When it's conservative, all the line integral stuff works out really well. So let's show that this vector field is conservative. Show it is conservative. So it's asking us to take the curl. It's asking us to take the curl and verify that it equals 0, the 0 vector. So this is going to be partial x, partial y, partial z. This is going to be y squared z cubed. This is going to be 2xyz cubed. This is going to be 3xy squared z squared. Okay? And so, what do we get? This becomes I hat times the determinant partial y, partial z, 2xyz cubed, 3xy squared z squared. Becomes minus j hat times the determinant partial x, partial z, y squared z cubed, 2xyz cubed. This becomes negative j hat times something. And this becomes k hat times the determinant partial x, partial y squared z cubed, 2xyz cubed. And this becomes k hat times something. So up here, this becomes partial y of this. So this becomes 2, okay, so it becomes 6xy z squared minus partial z of this guy. So it becomes 6xyz squared. So this goes to 0. Over here, partial z of this becomes 3y squared z squared minus partial x of this becomes xyz cubed. Did I mess something up here? J, so partial x, partial z. Oh yeah, this should have been a 3x y squared z squared over here. I put the wrong entry in there. So when we do partial x of that, it becomes 3y squared z squared. So this goes to 0. And then partial x of this just becomes 2y z cubed. Partial y of this just becomes 2y z cubed. So this goes to 0. So the curl of this function equals the 0 vector. So we have shown that it's conservative. Why do we care if it's conservative? Well, the line integral behaves like the normal integral. In some sense, we have a fundamental theorem of line integrals for it. So let's find a potential function. Potential function is this function f, such that its gradient is equal to some conservative vector field. So how do we find it in general? Okay, let's say we have, let's use the old vector field that we showed that was conservative. We showed that this was conservative here. We showed that this is equal to a conservative vector field. So by definition, that means this is equal to some gradient of some f. But that means that this is equal to some partial f, partial x, some partial f, partial y, some partial f, partial z. That means component-wise that partial f, partial x is equal to this, y squared z cubed. And that partial f, partial y is equal to this 2xy z cubed. And that partial f, partial z is equal to this 3xy squared z squared. So let's take a look at this guy. Okay. Notice that partial f, partial y equaling 2yz cubed x. Oh, wait. We are going to look at that guy, but first we want to actually not look at that guy first. Not this one first. We'll look at this one in a second. Let's look at x first. Okay, so I'll just rewrite it. Partial f, partial x equaling y squared z cubed. Okay. Notice that I could take the integral of both these sides here. All right, I can take the integral of both these sides. So what would that give us? That would say integral of partial f, partial x dx is equal to the integral of y squared z cubed dx. Okay. So the fundamental theorem of calculus would tell us that this is what we get here. Y squared z cubed x when you take the integral of this with respect to x. Plus, here's the kick. Here's the kicker. That you get some function g of yz equaling to your f xyz. Why is that happening? Well, when you take the integral of this, it should undo the partial x. So that's why it should equal your normal pre-derivative function. This is just your good old taking your integral dx. What is this g of y, z? Well, this is here because if I were to travel backwards in the calculation, if I took partial x of both sides here, I'd get partial x again. I should get y squared z cubed, right? Like we had before. So this g of yz, it could be a number, it could be a constant, but it could also be any kind of expression with y's and z's in it. Because when we take partial x of both sides, that differential operator thinks this is a constant, so it makes it go to 0. So in general, it can exist there. Because when we take partial x of both sides, it would just bring this down to here. Whether that g of yz is just an added constant, like +2, +5, -8, or whether it's some weird function like y cubed plus z squared divided by z to the 14th power. Partial x will delete that thing. But we keep it there in general because it's true and because it'll allow us to derive the potential function. Okay? Notice, yeah, okay, good. So now let's think about what partial f, partial y is. Now we will address this guy. Partial f, partial y is equal to 2xyz cubed. Take the integral of both sides again. That means the integral of partial f, partial y, dy should equal the integral of 2xyz cubed dy. This should equal 2xy squared z cubed over 2. Cancel, cancel. It should equal xy squared z cubed. But don't forget, this equals to our f of xy, z. And again, it should have okay. What am I doing? Okay, I want to backtrack. Because I went down the wrong rabbit trail here. Let's go back to just discussing this function here. Partial f, partial y is equal to 2xyz cubed. Okay. Notice that partial f, partial y is equal to this, but it is simultaneously equal to 2yz cubed x plus g with partial. So I would say partial g of ryz partial y. Say what? Well, once we got here, right? We said we know what partial f partial y is equal to. It's this. So we put this right here. But then we also said, well, we can also arrive at this expression by taking partial f partial y on both sides here. Partial f partial y here, and partial f partial y here. So this becomes 2 y z cubed x plus partial g partial y. So that's how we got to this right here. Okay. Yeah, I went down a weird rabbit hole there. Okay, but that's what's going on here. And we can just shorthand call this g sub y, meaning we took partial y of g. Okay. What does this buy us? Notice that this and this are the same, right? So if we just look at this equation alone, just this equation right here in the squigglies, if this and this are the same, I can subtract this from both sides, and I get this g sub y of y g is equal to 0, meaning it was a what? Well, meaning that it doesn't depend on y. So that means g of yz is equal to some hz. So it in general could have had expressions in y, but this has shown that it doesn't. So now it can either just be an old number like 4, 5, 7, or it could have an expression purely in z's, like 3z cubed plus 5z squared minus 13z, stuff like that, anything like that. This information allows us to determine that this is true. So then let's look at partial f, partial z. We have that partial f partial z is equal to 3xy squared z squared. Okay. But notice that I erased it. I wish I didn't erase it. I had right here that f of x, y, z had equaled y squared z cubed x plus our g of yz. Then we determined that this is just some h of z. Okay. So then this is going to be equal to partial z of this expression. Because this is the same thing as partial f partial z. So notice that this ends up equaling 3z squared y squared x plus h prime of z. Oh, but would you look at that? If we just focus our attention on this equation, this is the same thing as that. Subtract from both sides, and so we get what does that mean? Well, that means h of z is not dependent on z. So what must it be? What kind of a function? It does depend on y, it doesn't depend on z. What kind of a function does it have to be? Excellent. That's absolutely right. It's just a constant. It's just a constant because every time we take the derivative of it, it is equal to 0. It must just be a constant. So that implies that f of x, y, and z, we knew that it equaled this, right? And then we determined that it equaled this plus hz, but then we determined that this is some constant, let's say k. So that means this is f of x, y, z is equal to just this y squared z cubed x plus some k for some constant. And you're done. You found the potential function. That is the function such that when you take its gradient, it will equal this original vector field. And this will take some practice. It's kind of like convoluted, but it's not that bad. All you do is, under the assumption that it is a conservative vector field, you set each of these components equal to some partial f partial x, some partial f partial y, some partial f partial z. And you start integrating and seeing what they equal, and then start setting other equations equal to each other and start extracting more and more information.
So do you have to start with partial f, partial x to integrate it, or can you start with any of them?
That's a great question. It shouldn't matter. Yeah, that's a great question. It should not matter. You could have started with the other one, and it shouldn't matter. That's just how I had it in my notes. Mm-hmm. But it technically should not matter, because if this function is equal to some y squared z cubed plus x plus some k, then it equals that whether we analyzed it first with partial f partial x or with partial f partial z. If the method in which you're doing this changes the end result, something's going on with the method. Now, time to talk about divergence. The divergence div of some f defined as this. It uses a dot product, so the output is a scalar. What does this mean? Oops. Some f if it's like some p, some q, and some r. So then it's going to be equal to partial p, partial x plus partial q, partial y, plus some partial r, partial z. It'll be the scalar of that. So, for example, what if our vector field had the equation xz, xyz, negative y squared? What is the divergence of that vector field? Well, it's partial p partial x, which is just a z, plus partial q partial y, which is just a xz, plus a partial r partial z, which is just plus a 0. So the divergence is just z plus xz. here's a theorem that the divergence of a curl, what do you think that's going to equal? The divergence of a curl is equal to 0. This could be shown by taking the dot product after we take the curl. You get that partial R, partial Y minus partial Q, partial Z business. And then you take the I can just show you, that's actually pretty routine here. I have enough time to do it too. Okay, so here's the proof of that. That's the same thing as I, J, K, partial X, partial Y, partial Z, P, Q, R. We know that then, we've done this before, and it gives us this vector. It gives us this vector, this partial R, partial Y minus partial Q, partial Z, comma, partial P, partial Z minus partial R, partial X, comma, partial Q, partial X minus partial P, partial Y. And then when we take the divergence of this, it's going to equal partial, because this thing right here, recall, is just partial X, partial Y, partial Z. It's this vector. So when we dot this vector, what we end up getting is partial X of all this partial R, partial Y minus partial Q, partial Z, plus partial Y of partial P, partial Z minus partial R, partial X, plus partial Z of partial Q, partial X minus partial P, partial Y. So this becomes partial squared R, partial X, partial Y, minus partial squared Q, partial X, partial Z, plus partial squared P, partial Y, partial Z, minus partial squared R, partial Y, partial X, plus partial squared Q, partial Z, partial X, minus partial squared P, partial Z, partial Y. Okay, so partial squared P, partial Z, partial Y is the opposite of this. So we cancel partial squared Q, partial Z, partial X by Clairaut's theorem. This is equal to 0. And this should actually not be the 0 vector. It should actually just be the 0 number. Because when you take the dot product, you should get a scalar. And that's why we're not getting a vector. We're getting just a number, 0. Okay, so one last thing. One quick last thing. Let's show that this vector field cannot be written as the curl of another vector field G. Let's show that this vector field F cannot be written as the curl of some other vector field G. Okay? So we do so by saying, well, when we took the gradient, or when we took the divergence, this is the divergence of our vector field F, we got Z plus XZ. And this is non-zero. Okay? So because of that fact, there's no way, so to show that this can't happen, we assume that it can happen and show that that leads to a logical error. Assume that it does happen. Let's show that this leads to a logical error. Well, notice that what we can do is take the divergence of both sides. This implies that we get the divergence of F is equal to the divergence of the curl of Z. But we know that the divergence of X is X plus ZX. Oh, but we know that the divergence of a curl, if the G is a conservative vector field, actually, the divergence, yes. So this becomes 0. But we assume, but this is non-zero, so that's a contradiction. This equation is a contradiction. So this implies that this cannot happen because it messed something up logically. I didn't get to the Laplacian, and I didn't get to Green's theorem in vector form. That, the rest of this chapter's information, it's up to you guys to teach yourself. It's really sad, but when you only have 50 minutes and it's Calc 3 material, you either thoroughly go through some of it and not all of it, or non-thoroughly go through all of it. And it's just kind of confusing then. So keep up the great work. The divergence of the curl is 0. The divergence of the curl is 0, yes. Yes. We showed that before. Yes, ma'am.
I have a question.
Yeah.
Are we gonna find out how we did on the last exam before we do our final?
You should. But are we having class on Wednesday, or there's no classes on Wednesday? So this is technically the last day of class? Oh,
I mean, it's the last Monday, Wednesday, Friday day.
I see. Yeah, I could grade them, today or tomorrow. Do you want to see the exam, or do you just want to see the score,
I mean,
or both?
I would kind of like both.
Both?
If that can't happen, I would
Okay,
like
well,
to see the score.
My office is right there, and while I'm here, you once I've graded it, feel free to swing by or send me an email saying, hey, I'm free during this interval of time. Is there a way that I can swing by and look at my exam, or actually just take it, just pick up your exam?
Okay. And then is it still okay if since I have back-to-back finals, if I start?
Absolutely.
And then come back?
Absolutely. 100%.
Okay, I just wanted to make sure.
100%.
Okay.
I want to give you all the opportunity to do well, all of the opportunity.
Thank you.
Yeah, you'll have as much time as you want.
Okay.
Of course, not like, 10 hours.
Right.
Or else I'll just have to like bring some pillows and a blanket and sleep here. Yeah.
Thank you.
No problem. Okay, also, is the final still all of chapter 13? Could I also get my exam? Yes, you can. So far, we are gonna include all of chapter 13 on it. I may or may not change my mind. Who knows? We'll see, but probably won't. It's gonna have all of chapter 13 on it, absolutely. Which I know is really hard. It's a lot of information crammed in a short amount of time, but I know you guys can do it. You can get your exam, absolutely. Just send me an email saying, hey, I'm free during this time interval. Can I swing by and pick up my exam? And we'll figure something out. Sound good? Does that thumbs up mean you heard me? Okay, good. All right. Take care.